Hello everyone, welcome to the lecture number 5 of diodes. This will be a brief lecture. We're going to do a couple of example problems of the concepts that we talked about, and briefly we're going to talk about the current that flows through the diode and the reverse bias condition, whether any current flows through the p junction or not at all. So we're going to discuss that. For our ideal diode, we assume that it will be an open circuit, so nothing flows. Now we're going to talk about what will happen in the real diode. All right, so let's start with an example. So silicon diode of 1 milliampere displays a forward voltage of 0.7 volts at current of 1 milliamperes. We have to find the value of Is, the scaling current. So this is A part. So let's solve this. Right, so we have a silicon diode that for which the forward voltage is 0.7 volts and the current that will flow through it will be 1 amperes. So we know that I equals to Is e raised to power V over Vt. Again, we assumed n equals to 1 if not provided. Right, so since I'm interested in finding the value of Is, so Is will be equals to I e raised to power minus V over Vt. Alright, so I know the value of I over here is 1 milliampere, 10 to the minus 3, 10 to the minus 3, e raised to power minus V. Applied voltage is 0.7 volts, so it will be minus 0.7 divided by Vt. Vt is 25 millivolts, so it will be 0.025. So if we will solve this, we're gonna come across Is equals to 6.9 into 10 to the minus 16 amperes. So this will be the scaling current, the saturation current that will be flowing in addition to the diffusion current when the conduction will start to happen at 0.7 volts in the forward bias condition. Similarly, let's again find Is when a current of 1 ampere will flow at 0.7 forward bias voltage, right? So essentially we will do exactly the same thing. Our Is will be I e raised to power V over Vt minus now it will be 1 amperes, e raised to power 0.7 over 0.025. So the answer that is going to come out to be 6.9 into 10 to the raised to power minus 13 amperes. In both of these cases, you can interestingly realize that the current that is flowing through the diode in the forward bias condition is extremely larger than the scaling or the saturation current, the condition that we discussed earlier. So the take-home message from this example problem is that we can use this equation to find out the values of the scaling current as well that is flowing through the diode in the forward bias condition. And we saw that this current is usually extremely smaller as compared to the diode current. Okay. Now we are going to discuss a couple of quick concept, and then we will do one more example problem in this lecture. Temperature effects. Temperature effects. We discussed earlier that our Is, scaling current, and the thermal voltage are both temperature dependent. Right, so let me make a plot here. So this is current I that is flowing through the diode. Here is the voltage, and I'm gonna make these two curves here. This is I naught. The difference over here is 2 millivolts, and this is at the temperature T1, this is at the temperature T2. T2 is greater than T1. Right, so what does it say? This plot says that if we have increase in temperature, the voltage that is required to put the diode in the conduction will be reduced by 2 millivolts. So for every degree Celsius rise in temperature, there will be a reduction of 2 millivolts, right? So it will be minus 2 millivolts per degree Celsius rise in temperature, right? So for a constant diode current, the voltage drop across diode will decrease by 2 millivolts for every 1 degree Celsius rise in temperature. Excuse me. Right, so for example, you're operating a diode in the forward bias condition. It has a constant diode current, and what will happen is if you will increase the temperature 1 degree Celsius, that potential drop across the diode will drop by 2 millivolts, right? So essentially, in terms of the conduction, looking at this plot, we can also see that the voltage required, the threshold voltage, is decreasing also by 2 millivolts for every degree rise in the cells, for every degree rise in the temperature for the operation of the diode. Okay, now we are going to talk about reverse bias condition. So up till now we have talked about the forward bias condition. Now we will see what the diode in the reverse bias condition, right? So this was IV characteristics of the diode that we studied in the last lecture, and we can see that even in the reverse bias condition, there is, for a small voltage value, there is no current, and then there is some form of a constant current that is flowing till the diode breaks down and enters into the breakdown mode. So we are going to discuss this IV characteristics now. Also importantly, the equation that we derived over here, this equation was valid for both forward and the reverse bias. That it's not valid for the breakdown, but it's valid for both forward and the reverse bias conditions. So we're going to use the same equation to find out what is the current that flows through the diode in the reverse bias condition. Okay, so under reverse bias condition, right, if the potential drop across the diode is less than 0 volts, and let's make another assumption. If this voltage that we have applied is sufficiently larger than the threshold volt, which is 25 millivolt at 20 degrees Celsius, let's find the diode current. Right, since it is less than 0, so this means that the diode is in reverse bias condition. We know that I equals Is e raised to power V over Vt minus 1. Now if this condition will be true when modulus of V is much larger than the threshold voltage, we can simplify this equation, and this equation will become, the current will become equals to minus Is. So this shows that in a reverse bias condition, the diode current is constant, and it is almost, if this condition is met, then it is almost equal to the saturation current, and that is why this current is known as the saturation current, right? So in reversed biased condition, diode current is constant, and reverse direction of Is. Right, since it is constant, so that is why, it's called saturation current. Now for real diodes, the reverse current let's call it as IR, is usually larger than the scaling current. Over here, with these assumptions, we saw that our diode current or the reverse diode current is equals to minus IS. This negative shows that our current is flowing in the negative direction, the reverse direction of the scaling current. However, for the real diodes, our reverse current is usually larger, slightly larger than the scaling current, right? And that is also true when if our thermal voltage increases, then our reverse current also increases. No, actually, this is the reverse voltage. So if reverse voltage, right, so it is this value of V. If the reverse voltage increases, the reverse current will increase as well, right? So that is why, as you can see from this plot, as the reverse voltage is increasing, there's a slight increase in the reverse current that is flowing through the diode. Another important in terms of temperature effects, that the scaling current doubles for every 5 degrees Celsius rise in temperature. And reverse current doubles for every 10 degrees Celsius rise in temperature. In terms of temperature effects, please note down that since our under reverse bias condition, scaling current plays a major role. So both scaling current or the saturation current and the reverse current are temperature dependent. So for every 5 degrees Celsius rise in temperature, the scaling current doubles, and for every 10 degrees Celsius rise in temperature, the reverse current will double as well. Okay, so we talked about the reverse bias condition. Let's quickly talk about the breakdown region, and then we will do a quick example as well. Right, so in the reverse bias condition, we still have some current that is flowing. It's not a completely open circuit model. We have a very small current that flows, and that current is majorly dependent on the reverse current. And we also saw that as the reverse voltage, as we can see it from here, as the reverse voltage is increasing, our reverse current is also increasing till it reaches a particular voltage value, which is called as a breakdown voltage, beyond which we usually get this avalanche effect. And the diode enters into the breakdown region. And we have this huge amount of the current that flows, which is we are going to exploit this condition to build voltage regulators. We're gonna discuss that. Important thing in the breakdown region is that since we have a very huge amount of current that flows through the diode, so this does not mean that the diode will be broken down or will become ruined until and unless we will limit this current. We have a huge amount of current that flows through the diode. If we can use this external circuitry, simple resistors, to limit this current down, and then we can potentially use the diode. We will also see in the next lectures how we can exploit this condition to build certain circuit or in certain applications. So very quickly in the breakdown region, as reversed bias voltage increases a threshold, this threshold is different than the threshold for the conduction. A certain threshold value, it enters into breakdown region with increased reverse current. We saw that we have an increased reverse current that will flow through the diode. Importantly, diode will still remain operational provided current can be controlled by external circuit. So the huge current flowing through the diode does not mean, huge reverse current flowing through the diode in the breakdown region does not mean that the diode is broken down. It can potentially be broken down if it is not limited. So we just need to limit that current by external circuit, simply by the resistors. And we have a and usually the data sheets of the diode gives the breakdown current value. Alright, so this is it with the breakdown region. We're going to do one quick example to wrap up our lecture. Again, in the breakdown, you also saw one more term. We are going to discuss this term in the next upcoming lectures. This VZK, this is usually called as over here. I'm just going to introduce the term. Over here, the Z is the Zener and K is the knee. Knee is because of this thing, and so Zener is a special type of diode which is specifically designed to operate that diode in the breakdown region. And this is specially used for the voltage regulators. Just introducing the term over here, we're going to discuss in detail in the upcoming lectures. All right. So let's do one more example. All right. So we have a diode here. Plus minus V. V is the voltage appearing across the resistor. As you can see from here, the diode is reverse biased. Right, so if value of the V equals 1 volt at 20 degrees Celsius, find the value of V, or this V, at 40 degrees Celsius and 0 degrees Celsius. Right, so let this be A and this be B that we want to find out. Okay, so in A, so let's first find out the value of the reverse current when V equals to 1 volt. Value of the reverse current at V equals to 1 volt will be 1 volt divided by 1 mega ohms. So 1 over 10 to the 6, 1 microamperes. Right, and then now we know that reverse current will double every 10 degrees Celsius rise in temperature, right? So this was 1 micron amperes at 20 degrees Celsius. So this means that IR at 30 degrees Celsius will be 2 micron amperes, and IR at 40 degrees Celsius will be 4 microamperes. And when IR will be at 40 degrees Celsius will be 4 microamperes, the potential drop over here across the resistor will become equals to 4 volts. Okay, so similarly, IR at 20 is 1 microamperes. So IR at 10 degrees Celsius will be, so if it is doubling for every 10 degrees Celsius rise in temperature, it will halve for every 10 degrees Celsius drop in temperature, right? So IR will have for every 10 degrees Celsius drop in temperature. So reverse current at 10 degrees Celsius will be 1 microampere divided by 2, 0.5 microampere, and IR at 0 degrees Celsius will be 0.5 divided by 2, 0.25 microamperes. And the potential drop at that point in time across that will be equals to 0.25 volts. So this is how you can find out these values in terms of temperature effects as well. Right, first we find the reverse current at a specific voltage that was given. Then we knew that the IR will double every 10 degrees Celsius rise in temperature, so we essentially doubling it up. For drop in temperature, we reduce it to half. And the reverse current, when the reverse current will be 4 milliamperes, we saw that at 1 volt our reverse current was 1 microampere, right? So when our reverse current will be 4 microampere, the voltage drop will be 4 volts. When it will be 0.25 microampere, the voltage drop will be 0.25 volts. All right, so with that, this ends our lecture today. And in the next lecture, we are going to solve some of the diode circuits, and I'm going to give you 3 different models of the diode. Very specifically, we have an ideal diode model we talked about. We have 2 more models. And we already started developing the theory for that. One is the exponential model that we saw, in which our curve looks like something like this, and then we're going to have another constant voltage drop model. Rather than assuming this exponential relation, we are just going to assume it a constant voltage drop model. So we're going to discuss these models. We're also going to see how we can solve different circuits using the graphical and the numerical methods. So we're going to do some of that in the next lecture. All right, so with that, thank you so much. I will talk with you in the next lecture. Thank you. Bye-bye.